Okay, so we're going to learn two series tests today. The first one is the comparison test. So for comparison, we're going to compare to a series that we already know how it behaves, and the most well-behaved series that we know are the geometric and the p-series. So when we were going to learn two today, comparison and limit comparison, and for these, most of the time, we're going to compare to geometric and to p-series. And so for the comparison test, it's just a direct comparison, so it's sometimes called direct comparison. And what it's saying is, if you have a series that is smaller than a series that converges, then your series is going to converge as well. And that makes sense, because if the series has a limit, like it's not getting any higher, and your series is smaller than that, then it's also going to be negative. Okay, so if the series is smaller than a series that converges, your series converges as well. The other side of that is, if your series is bigger than a series that diverges, your series is going to diverge as well. So basically, if you're bigger than something that goes to infinity, you're going to have to go off to infinity as well. Okay, so those are the two main things. If you are smaller than something that diverges, you don't know anything. Maybe you go to infinity too, maybe you're down. Okay, and so that's the premise, and we're going to be comparing to mostly geometric and p-series because we know how they behave. Okay, so our first one is this guy. So it's the summation from 1 to infinity of 2 over 3 to the n plus 1. And what you're going to do is basically take away any plus 1s or anything like that. So what I'm saying by that is I'm going to just get this down to 2 over 3 to the n. Okay. Because if I do 2 over 3 to the n, so basically you just get rid of, on any of these problems, you're going to get rid of the things that are added, stuff like that, so that it will just look like either a geometric or a p-series. What does this look like? Does it look like a geometric or a p-series?
P-series.
Really?
Well, not quite.
Well, let's look at a p-series. It would look, here's what a p-series looks like. It looks like 1 over maybe n squared or 1 over n cubed or something like that. Notice the n is the base, and here it's the exponent. Yeah, so a geometric, the exponent is what you have. So this one is really like having, if you just took the 2 out, you could actually do it like 1/3 to the n. So then that's a geometric.
That was quite
yeah. Okay, so I'm not saying these are equal. What I'm saying is that this one is what I'm going to compare it to.
Okay.
So these are not the same, but they're kind of close.
That's why they call it the comparison.
That is why they call it the comparison. Good. Okay, and so if you think about this, this is a geometric series. What's R equal to?
1/3.
1/3. So does that mean that it converges or diverges? Converges. Okay, so now here's the deal. We got to see, is this one smaller or bigger than that one? Okay, so if you're dividing by just a little bit more, that makes your number smaller. So if I add 1 to the numerator, that would make the number larger. But if you add 1 to the denominator, it makes the overall number smaller. Yes. So we are smaller than something that converges, so all we have to do is say that that our series converges by the comparison test. Okay, you will, again, see it called direct comparison test sometimes.
So we need to show that the geometric series converges by the geometric series first, and for the series test, and you get right to it.
Oh, sorry. You do have to say what that one does.
You have to say that it converges by the geometric series test, or geometric series.
Well, I said geometric series which converges because R is equal to 1/3, which, if you say it the way you said it, is the same thing. You have to say it in some fashion. Okay, so I have to do something that indicates that I'm showing that what is smaller than converges, and I thought that was good enough. Yours was just slightly better. Yes? Okay, because you're just comparing. They're the same, except this one has +1 in the denominator. So if you're dividing by a slightly larger number, so like if you divide by 5 instead of by 4, that makes the number smaller.
It's like y has a greater magnitude than this.
It's like comparing 1 over 5 and 1 over 4. If you make the denominator larger, then the overall number is smaller. So anytime you see, and this is like a common, like this is usually a big sticking point, is whether people get which way they get the inequality. So notice if the denominator is larger, that's the one that's going to be smaller, because you're dividing by a bigger number. If the numerator was larger, whichever one, if they were the same except the numerators were different, if the numerator gets larger, it makes that number larger. But if the denominator gets larger, it makes the number smaller. Question? Okay. Give me a second.
Take out the 2.
Mm-hmm.
That's 1/3. Which is just R.
Mm-hmm.
But there's not any 1 originally. Take out the 2.
Uh-huh. But there has to be, so like if you did, I see what you're saying. So if you do this originally, you're saying there's a 1, but it's not to the n. Oh, sorry, this is a 2.
Yeah.
But 1 to the n is the same as 1. And so that's why it's okay. Well, you can even look at it as this, though. You could say that 1 is still there, but what is this 3 representing? It is a third, because it's dividing by n. So, like, even if you're not thinking it's this n that's doing it, a 3 in the bottom is essentially a third already to the n. That might make more sense.
Yeah.
Okay.
Just like those 1 to the infinity, that's one of them.
That's true. That's true. But, yeah. But also, yeah, I see what you're saying. But also, if you look at it fractionally, it's one of our one that converge. We know it converges. So, yes, 1 to the n, but when I changed from this to this, I didn't say that converged. It was the fact that it was 1/3 to the n altogether that made it converge. So that the 1 over 3 to the n being the same as 1/3 to the n didn't really have to do with it going to infinity yet. It's what you do with it after that. Okay. All right, so this guy, when I look for what I'm going to compare to, I'm basically going to get rid of the 3. Okay, so what I'm going to compare to is just get rid of this, get it down to the bare basics. No, because that's what it generally looks like for a p-series, is it's 1 over n to the something. So just kind of remind yourself for the p-series, we're at p less than or equal to 1. Okay, so this is a p-series that diverges. Okay, so what is my series, smaller or larger? So do I know anything? Okay, so no conclusion here. All right, now, to be honest, if I'm in this situation normally, if this doesn't work, the very next thing I do is the limit comparison test. But I haven't taught you the limit comparison test. So what I'm going to do, because I haven't, is I'm going to try to compare it to something else. Okay? I'm going to try to see, is it bigger than something I know diverges? Okay? So here, what you're not going to like is I'm going to pull different series that I know out of the air and try to compare. Okay, so instead of n to the 1/2, I'm going to compare it to n, 1 over n. Okay. And I don't know which one's bigger, but that's another something that I know how it behaves, so I'm going to compare. And I'm going to compare by looking at the calculator. Okay, because this is going to illustrate another point about direct comparison by doing this. Okay, so what I want you to do, did you need the paper back?
No, 40 seconds. Okay, thanks. What exactly did you articulate that you did not?
Clearly, the universal sign error. I need to see that paper a little longer.
I'm good.
Okay. right, so the two things I'm going to graph are the 1 over 3. Thank you.
My name's Jason.
Okay, and the other one I said was just going to be 1 over x. Okay, and so you just kind of look, and which one, I mean, what am I hoping? Well, but 1 over x, what does it do?
Continuous
It diverges, so it's only of use to me if I'm bigger than something that diverges. Does it look like I'm bigger?
Yeah.
It doesn't. It looks like I'm smaller. I definitely am smaller here, but I can't really tell over here. So I'm going to go to the table. I'm not going to. Okay, and so I really want the purple one to be bigger. So right now, you kind of have, if I can see this a little better. Okay, want the purple one to be bigger. Is it bigger there?
No, it's not bigger anymore. Oh no.
Okay. Is it then?
Oh, it's
At any
getting
point?
bigger again. Yeah.
Okay, so when does it start being bigger?
After
From 6 on? Okay, so here's the thing. If it's bigger from, it can be from any point onward. If I can say it's from there, if it's bigger from some point onward, that's good enough. It doesn't have to be larger the whole entire time. Now, it can't fluctuate up and down, up and down. Okay, but if I know that my series is bigger, and doesn't look like it's overtaking
looks
it, that
bigger.
tiny purple right there,
It looks bigger.
you get on down? Okay, so if I know that my series is bigger than a series that diverges from some point onward, then I can say it diverges. So that's what I'm going to do here. And so,
And is 1 over x like typically the thing that you would use in this situation?
you're always going to be comparing to something you know, which is always going to be either a piece series or a geometric. So as far as choosing this one, to be honest, if my direct comparison did not work, and you just gave this to me on an average day, this is not what I would do. I wouldn't compare with 1 over n, I would change the limit comparison. So usually if I know what to compare it to, direct comparison doesn't work, the limit comparison does, and I wouldn't be grasping around for other things like 1 over n to compare to. But it's nice because it does let me illustrate to you that from some point on. Okay. So, is this still technically comparison? Yes, this is. So I'm going to say, so the series converges. Now I do need to say this diverges. Oh, I need a summation sign too. Problems. This diverges, and you can say, because it's a harmonic series, that's the thing with the P series. If it happens to be P equal to 1, you can say that it diverges because it's a P series of P equal to 1, but you can also say it diverges because it's a harmonic series. It's just considered to be a well-known series. And I just wrote the wrong conclusion. If you're bigger than something that diverges, you diverge. So the series diverges by the comparison test. Okay, so you do have to give some indication that you know the behavior of what you're comparing to. But again, these are known rules, so it's not really a proof of it because they're considered tools we have in our toolbox. Yes?
So if this test fails, you just go straight to the limit comparison test.
That's what we should
So
do.
what's the point of this one? You just go straight.
Well, the point is there are many, many tests that work for the same point. Because this is shorter. Like the comparison test, the limit comparison, I have to perform a limit, which is more work. But if you can already tell, there's no point having to calculate the limit.
Yeah.
So that's the point of this one. It's shorter. But there are multiple problems that can be solved with different tests. So when I grade your test, I have to look and see, what have they done? All right. So when I look at this one, okay, first of all, if you see factorials, you're not going to prove it with the test I'm about to do. Generally speaking, the rule of thumb is for factorials, use ratio tests. It's the easiest test anytime you see factorial. But it can be done with other tests, and I need some more that I can do with comparison tests. So I'm going to do it with a less convenient test. Okay?
If you do it with like this method,
It's totally right. Okay, there's multiple I'm not showing you any methods you can't use. I'm just saying sometimes there's a better way, and I just haven't shown it to you yet. Okay, so the only thing I have in my toolbox right this second, I don't have ratio tests in my toolbox, is I have to compare this to something I know how it behaves. So I'm actually going to write out a few terms so I can see, like, if I think it's bigger than something that diverges, or if I think it's smaller than something that I know converges. So that's kind of my goal here. So I'm just going to write out the first couple of terms. So if you put in 0, what are you going to get in the denominator? 1. If you put in 1, what are you going to get in the denominator? Put in 2. Put in 3. Put in 4. And one more, put in 5.
120.
Okay. All right. So I need something to compare it to. I'm going to tell you what I'm going to compare it to. And you're going to say, how do you come up with these? I'm going to say, you just have to know different things, the behavior of different series that you could possibly compare it to. And again, I wouldn't. I would probably use a ratio test. Okay, so you're saying, do you see the logic? What I'm comparing it to is a known series. What kind of series? It's geometric. Does it converge or diverge? It converges, and you know that why. Okay, so I must be hoping that what I've got is less than that. Okay, so I'm hoping. Or technically less than or equal to. So let's put in a couple of terms. If I put in 0, what will I get? Okay, and then once you know the first term, because this is just 2 times 1/2 to the 0, you're just multiplying by half every time, so you don't have to like bother substituting in. So then the next one would be, keep going, keep going, 2 more. Okay, so let's look. Okay, is that term smaller? Well, I want that one to be smaller than that one. Okay. Smaller or equal to? Smaller or equal to? Smaller or equal to? Okay, and also think about it. We know that the factorials grow faster, right? So if they're in the denominator, these numbers are going to be smaller than an exponential. So that is a way to have thought, oh, this is an exponential. Probably when you compare a factorial to an exponential, the exponential grows faster, but it's in the denominator. So it makes it small. Yes.
I think like I wasn't paying attention for a second when you showed why how you got like this the thing under like
I proved it.
so you
Be
just
quite honest.
plotted
Yes.
three-
Okay, so coming up with, so the very valid question is, okay, yeah, I believe you, that's smaller than that, but how on God's green earth did you get that?
yeah, like
Okay. And so that would be very difficult to come up with. But you would at least, that's what I was kind of saying, is you at least know that factorials grow faster, so you might start to compare it with something that was a geometric, just because that's exponential, and it doesn't grow as fast if you talk about the denominator. As far as this particular one, I mean, it's just kind of a shot in the dark. The halves there is pretty much, I probably could have done just about anything for this, but I wanted the 2 to kind of start out larger than the 1, so it's kind of, yeah.
So, like, on a test, would the comparison function be, like, given, or would you still
No, you'd still have to figure it out, and since it's difficult to figure it out, I would say use a ratio test for this kind. So I'm acknowledging that coming up with something like this is difficult. I mean, it would take a while. And you know, on a test, you don't really have time to fiddle around with the types of series and what it would do. So don't worry. You probably won't have to come up with that. Typically, what you're having to compare to is just something where you're just making it simpler. Okay? So when you get to this, I'm going to do it again. You're going to be like, well, of course you would use a ratio test. Okay? But for now, we are smaller than something that converges, so we're going to say that our series converges by the comparison test. So I'm hoping that you were fairly satisfied with the comparison test on this one, okay, because you're just comparing to a known series. Here, you would have been happier with me if this had resulted in something good, but you weren't happy because I had to come up with a different series. Okay? The deal is, on these, if this doesn't work, we're going to go to limit comparison. So now I'm going to show you what a limit comparison test is. Okay? All right. So here is the limit comparison test. This is on your sheet that lists all your series. And yeah, you're really going to have to know everything this says. All this stuff, you really have to know it. Okay? So you start learning these tests now. Don't wait. Okay? Also, on my Matthew YouTube channel, I do have one video. You'll see it's my most watched. Now, that doesn't take much because it's just about views. Maybe 25. I don't know.
Hey,
So-
there are more than 25 people in this class. How much money she earned from that? Pennies.
I'm literally not ready. No. So I do have one video that just describes all the series tests and gives you an example of each one. Okay. And so that might be one that you might want to watch in preparation for the test. There are a few examples that will be called series ones. Yes.
So I would just look up Matthew Cathy, and I would just see some video that
Yeah.
would
So
say.
there is another Matthew Cathy with a C.
No.
No,
We
well, I am possible.
I'll do this.
But there's not another Matthew Cathy with a K. I don't.
Do you have more subscribers?
I don't care about anything else.
No, it's a
Circle down.
competition.
Well, I got care.
Who is subscribing to Kathy?
Exactly.
Quote Cindy.
Okay.
Matthew Cathy with hate.
Said,
Yeah.
I don't want to.
Let's not do that. I understood what you meant, but still, let's not do that.
This is
No.
I would not do it.
Okay. Take those glasses off. It is not a suit. Therefore, you cannot wear the glasses. All right. So here we go. Emily, we apologize for all of this. Yes. Okay. All right.
We got pushes.
What did I just say?
say?
Yes, we're still recording. Okay. All right, so here we go. Limit comparison test. Okay, so the limit comparison test you're going to do if you know what to compare to, which is pretty much a P-series or a geometric series, but you get an inconclusive. Okay, so like you're smaller than something that diverges. You're going to change to a limit because a limit is basically telling you which one is converging faster. Yes?
So you always do comparison first, and then if it doesn't work, then you go to limit. You never
Yes.
start.
You can start with limit. It works if the other one works. It's just shorter. Okay. So this one, what you're going to do is figure out something to compare to. The one you're comparing to is going to be B sub n. Okay. So I'm just going to write that. B sub n is what you are comparing to. Now notice when I say what, it's actually, I should say, the sequence. Okay, because it doesn't have a series by it. So you are comparing two series, but when you put into the limit formula, you're putting a sequence in it. You don't put a series into a limit formula. Okay, so you are finding a series to compare to, but you use the sequence of the series that you're comparing to. Okay, so you're going to take the limit as n approaches infinity of your sequence divided by the sequence you're comparing to. If you work that problem, and you get something that is positive and finite, then both behave the same. Okay, so if what you were comparing to converges, you converge to. If what you were comparing to diverges, you diverge to. Okay, so it behaves the same. All right, so some people, they get positive finite. There was somebody last year on this test, when they do the test right, they'd get positive finite and they'd say it converged every time. Not thinking about what they were comparing to, the behavior of it. Okay, so if you get your test wrong, you still know how to work a bunch of stuff, you can get a lot of problems wrong. If I have multiple problems on limit comparison test, huh? You don't get a lot of marks. You get some marks, but you lose enough marks to make you sad because you have the wrong conclusion. You don't understand the test. Okay, so positive and finite, they both behave the same. You got to remember that. And then you honestly, this is what you end up using the most is the first one. The second and third, they come up sometimes, but not as often. Okay, so if when you take the limit you get 0, if what you're comparing to converges, then yours converges also. if what you're comparing to diverges, the next one, if you get infinity for your answer, if what you're comparing to diverges, then your series diverges as well. Okay, so, and it gives you a little note off here to the side. Okay, it says if you get 0 and what you're comparing to diverges, you don't know anything. Okay, so notice,
So basically,
this is 0. If this diverges, you have no conclusion.
basically for the second one, it means that a sub n which we're comparing to is smaller than something converges because it goes to 0 and then denominator grows faster.
Yes, but B sub n is what you're doing.
Yeah. Yeah.
So yes to everything else.
And then 3 is like a sub n is growing faster than something that's growing.
Yes.
Okay, so
Exactly
that's
right.
basically just like
That's the logic of it. So if you understand the logic of it, it's easier to remember the
So
rule.
the first two are basically just the exceptions. Well, I mean the last two.
All right, so if we take a look at this now, determine the convergence and divergence. I'm going to do the same thing I did before, which is I'm just going to break it down. What do you think I'm going to knock off of this? Yeah, just so it looks a little more astute, yes. Okay, the constant I'm just going to take out. Now, I haven't said what's bigger. I don't know any of that yet. I'm just figuring out something to compare to. So the 2's out. I can do that same little trick I had a second ago. Is that the same problem that I changed? Okay. And I said I would really rather do this, so now I'm really going to do that. It's not similar?
This was 3 to the n plus 1. This was
Oh, okay. Okay.
Wow,
well, every slandering.
Okay, so the question is, which one's bigger?
One on the left.
Good job, dude.
Okay.
Luke doesn't know his left ring, just like he doesn't know his quadrants.
Ouch.
Okay.
This one's
So I'm dividing by a number that's a little bit smaller, so my overall number is larger. Okay, what's the behavior of this guy? Talk to me about this one. It converges. Okay, so it converges because it's a geometric series with r equal to 1/3. So I'm bigger than something that converges. Does that tell me anything?
No.
It really doesn't. Okay, I might converge to something that's a little higher, or I might diverge. So that's like, okay, I tried comparison, now I'm going to write out a limit. So I'm going to write the limit as n approaches infinity, and now when I said sequences, what I mean is I leave off the series part now. So I'm going to put my series divided by the one that sequence, divided by the sequence of the one I'm comparing to. So you leave off the summations. And again, trying to see what's growing faster, or if it's growing at a reasonable rate, if it's exploding. Okay, so the very next step, I'm going to change it to multiplication. And flip the second number. So some of you guys are not going to want to write that. You probably don't want to go straight to this. That's okay. Okay, so I've got the limit as n approaches infinity of this. So if I just do it right now, it looks like infinity over infinity. I could either L'Hopital it, or it's kind of, I mean, do you have a guess of what it goes to?
Yes, no, I'm guessing point.
Okay, 1 is actually the right guess. The reason is the -1 is kind of insignificant when you're going to infinity. Okay, so it's kind of like the leading coefficient rules, you know, like when you have n squared and n squared. It's 3 to the n and 3 to the n. So one way you can do it is by dividing each term by 3 to the n. The other way to do it would be to L'Hopital it, because basically when you L'Hopital it, well, you're still going to end up with infinity over it. It's still going to be gross, because this part's going to go away, but you're going to keep getting the ln 3 to the n. So yeah, I guess if you canceled it, that one should be alright. But then you'd have an ln of 3 over ln of 3 would cancel, so it just be so we'd be alright. I just hate canceling it before n goes to infinity. Just a little slightly mentally disturbing. So anyways, either way you want to do it, but the way I'm going to do it is I'm going to divide each term by 3 to the n. Dana's closet when she's gone for stuff for homecoming week. Kind of enjoyable. I did tell her that. You don't mess with Dana's stuff without telling her, even if she's miles and miles away.
So do people like push that like not all
You're actually selective to be, and that's actually a legitimate question because you can move stuff to college. You have such a tiny space. Like, if you know how in your room there's like all this stuff you don't usually wear. I would highly recommend you just wear that new sweatshirt on fine.
That's all you'll ever need.
But so it's like your prime stuff. You want to bring that, but if there's stuff you don't wear that often, you probably don't want to bring it. There's probably gonna be a bunch of stuff left in your old bedroom at home because even there'll be some, and you move it back every year or store it depending on how far away you live. But if you find that you're moving stuff back home and then moving it back to college and you never touched it while you were at college, that's less stuff for you to move. You should bring less rather than more because rooms are tiny. Some people's rooms are big. Most people's rooms are tiny. You just don't have the space. Yes.
Can I tell a real quick story about Dana from when we were in high school? She was,
Well, only if I give you the mic. So that
she was eating a pear. Dana was eating a pear in our preschool class, and I had never, at that point in my life, eaten a pear or really like seen anyone eat it besides the Star Wars movie when Anakin and Padme are on the place and he forces, like he uses the Force and she eats that piece of pear. That's all I knew about pear. I saw Dana eating a pear, and it looked very good. And later that day, like, I think I got my mom to like buy a pear or something.
This is it.
I like him.
Whole story brought to you live right here from HL Math class.
I thought
Oh my gosh, Jake missed it.
You have to watch it now.
You have to watch the whole video to see what you missed.
Give me a quick summary.
Say my hair.
Oh, that's your mother.
Okay, alright, so here we go. Okay, so what you're missing is the retelling of Alright, so here we go. I divided each term by 3 to the n. So these canceled. What happens as the n goes to infinity here? That goes to 0. So you get 1 over 1 minus 0. Okay, and as n goes to infinity, that just goes to 1. So this is positive and finite. So both series behave the same. Okay, which what we were comparing to converge, so therefore our series converges. I'm just going to say series converges.
Can you read us a little?
Yes, at least I hope I can. Positive and finite, so both, I could even put a therefore, positive and finite, therefore both series behave the same. So that says both series behave the same, therefore the series converges, which is what I was comparing to converged. Okay? Alright. This next guy. First of all, I just want to know if you have any thoughts on that.
That's gonna be a big hole.
I gotta go forward.
Okay, I have a proposal. It's definitely going to diverge. Why do you think that, Jake?
Because the power rule, we got n squared over n to the 1/2.
So if he's using power rule, what series test is he using? Term divergence test. Okay, so you're kind of the winner there because it's a lot easier than using anything else. Okay, so if you just compare the degrees, then we can automatically say the degree of the numerator is higher, therefore it's going to infinity. Okay. So cool that you can just lay it on the desk. Just, if you're wondering,
I'm
level,
just trying to do it now.
you're not there yet. Strive for it, but not yet.
It's time to do
Is
that.
there anyone that would want to do that?
No.
Paula was the only person who would
He just did not use his power. He used his power for good.
Therefore, the series diverges by the nth term divergence test. Okay. Now, if I was to compare, okay, and again, that was kind of the point Jake had to start with. He said the other ones are, kind of going to go along with comparison and going to infinity. But if I was to work this out, what do you think well, let me just tell you what I would compare it to. If I was trying to compare it, what I would do is get rid of the 1, so it was just n squared over n to the 1/2. Okay, you just get rid of that part, and then what is that? Yeah.
Quick question.
Yeah.
This kind of goes back to A.
Okay.
So if the harmonic series wasn't such a loser,
Right.
diverged,
Right.
would you be able to use the infinite divergence test to show convergence?
No. There are more examples in the harmonic. No, I don't have one to give you.
So they gotta be discussing the divergence.
Right.
That's a real
Yes. Okay, so this is what I would compare to. Do you want to try it just to see what it would look like?
Yeah.
Okay, let's try it. So that's what I'm comparing to, and what does this do?
That would converge. Diverge.
Okay, and so it diverges. You can think of it just because you could do the nth term divergence test on that. It's also a p-series because it's 1 over n to the negative 3/2. So you could also say this is a p-series, and p is less than or equal to 1. Okay, and so that guy diverges. So then when we go and do the limit test, limit comparison test, you take your sequence and you divide it by the one you're comparing to. Okay? And so this would look like the limit as n approaches infinity, n squared plus 1, I'm going to go n to the 1/2. Instead of divided by that, it would be times the reciprocal of that. And so this would look like the limit as n approaches infinity of n squared plus 1 over what? And what does that equal? Okay, so it's infinity over infinity. You can either L'Hopital it, 2n over 2n. From here to here, I added my exponents. So you can either do your horizontal exponent rules or you can L'Hopital it twice and get to 1. If it's 1, that's positive and finite. Behave the same. Okay, so behaves the same means diverged. And so it would be back to the same conclusion.
So people because compare the comparison one diverges.
Yes.
The other one is
They behave the same. So I didn't do a comparison. I didn't do a direct comparison.
that was
I could have said I was bigger than something that diverged, so I diverged. But I did a limit comparison. It would have been faster if I did what you just said. Because this is bigger than what I compared it to because it's plus 1 in the numerator. Okay, so we just showed we could do this one by direct comparison, limit comparison, this course, or nth term divergence test. Okay,
So we just found 3 tests for this one. 3. Right, you only need one. Pick one. It doesn't matter. Okay. Well, yes, but then I need back. Okay, so we're only going to do 2 more problems. And it's not this one. Don't look at this one. She's got the other side of my page. So that's ratio test. Ratio test is the best. Factorials and powers are the 2 main things for this. Okay, so remember, never, ever, ever turn your brain off because, well, it's a bad idea. But here I am leading you along. Let's do limit comparison. Let's do limit comparison. But look how short this one was, nth term. So, you know, even though I'm teaching you new tests, if there's a faster test, and you already know about it, you can do that. So you should always be thinking about nth term at the start of any problem because, you know, but looking at this one, would nth term help me on this one? No. Okay, so for comparing on this one, here's what I'm going to compare to. Okay, I'm just going to take this, and I'm really just going to care about the highest powers because that's what does all the controlling. Okay, towards infinity, the lower powers do not control as much as the higher powers. Oh, I'm going to get rid of the 3 too. Getting down just to the powers. Okay, and so that's the same as, so I just ditched any lower powers. Gonzo. Well, I'm just trying to compare to something. So if you're just trying to compare to, you're just trying to get what's controlling the function the most. So just take the highest powers if you've got a lot of powers. If you've got plus or minus some constants, that's not going to have much of an effect towards infinity. So you would ditch those as well. Get it down to just the basics. Now what I'm comparing to, do I know how it behaves? Converges. Oh, I lied to you. I have a free bonus problem in the middle. There's going to be 3 more problems. What? I know, I didn't print it. Sorry. Bonus for free. It's like you're that would cost at least another $100.
True.
All right. All right. So here's the UTC right here. All right. Anytime and you don't really know like which one's bigger. Okay, if you're not sure which one's bigger, just go to limit comparison. Okay, if it's not just clear, it's like the same plain thing, plus 1 or minus 1, maybe you know. Maybe you're not sure. I don't want it.
But like, if I did.
If you did and you were confident it was true from some point onward, you would be fine.
And you do have to draw the number, or would you say it's bigger or larger?
Well, the thing is, I didn't have to if it was algebraically obvious. If it isn't algebraically obvious, I would do something for proof, which would be yes. Oh, sorry. P series converges. P equals 4. Yeah.
P is greater than or equal to 1.
Yeah, you just want to do strictly greater than. Well, let's find out. I don't know. So if I don't know, I'm going to put mine divided by the one I'm comparing to. My sequence divided by the one I'm comparing to. And so I'm going to change it to multiplication, flip the second. One over into the fourth. So it was divided by 1 over into the fourth, so I changed it to times. It's your sequence divided by the sequence you're comparing to. So it's this divided by that. And that's technically going to both, I mean, if that's what you're thinking of. Okay. So this, I'm going to distribute my n to the 4th. So I have n to the 6th plus 7n to the 5th over 3n to the 6th minus n cubed. As you go towards infinity, what is that going to? Which is positive and finite. So they both series behave the same. And so ours does what? Yes.
Wait, how did you get 6? Oh, is that
Yes. Or you could look at how it 6 or 7 times.
what does that say in the O series?
That's what it is. It's fine. Yes. That's also true. Yes, it is reliable. Yes, there's a difference between brute forcing and finessing. You're exactly right. All right, so here's your bonus problem. Yes.
So, in the way that you get 1/3,
Yes.
do you kind of ignore everything except for the first thing, like the end of the 6th and the end of the
Yes. So you look at the highest powers, and then you're taking the coefficient. If they match, you're taking the coefficients. All right, so here's your bonus. Your $100 for free.
We get $100 if we get this right.
False.
You get a free problem for the value of $100.
That's right. Okay, so when you look at this and you think, what are you going to compare to? You want to try this one? I think you can try this one.
Why are we here? It's not over. I don't really think it's fake.
That's terrible. You have the same paper that I do.
I read a little.
Just compare to the
Alright, so you're going to compare it to my summation sign is really bad. Oh, that was actually the best one I've done. This is the one I did on my paper. I did that on my paper.
You forgot the two.
Those are pointless, David. You don't need those.
Yeah, you do need those.
They take up time.
You do not.
They make it look so much better.
Okay, but they're not
Unnecessary time.
aesthetic. They also
So this is what you're going to compare it to. You just take that silly little one off and then into the cube root of n, just into the 1/3 on top. And so you can change that to 1 over n to the 2/3 because you're just going to subtract, and so that would be n to the negative 2/3, but then you just put it in the denominator. So then that makes it P series, and so P series, P is less than or equal to 1, so that means it's going to diverge. Then you do big old division stuff, this one over this one. So, into the 1/3 over n plus 1 over into the 1/3. Ugh.
And could you have used comparison or not?
You could have. No.
Are you smaller than what diverges, or are you?
Oh no, you're smaller than what diverges, so you don't have. Over n, and you multiply
Oh, because I didn't have it on the
infinity of into the 1/3. What? Which way? This one? Uh-huh. What's the question, Sam?
And the fraction you have that has like the original one on top and the
Mhm.
one on bottom.
Yeah.
On the bottom, does that say?
It says into the 1/3.
Oh, okay.
It's just,
I
just, it looks like
Now, you
into.
could have put 1 over into the 2/3 instead of that, but it's exactly equivalent, so it doesn't matter.
Over plus 1 times n over n to the 1/3. Then those cancel out. So you get n over n plus 1, which will go to 1, which is finite, and what? Cool. Finite, I know, and positive. So, series diverges by limit comparison. I just concluded. What do you, no.
So when it's n over n plus 1, you just ignore the plus 1. It's just like n over n.
Well, you could either do like, so you could do like the power rule, so it's just like the same power, and so it's 1. Or you could do L'Hopital for it over and over again until you got it.
I have no clue.
No clue what that means, Jack.
Oh, that video.
Alright.
Oh, I gotta give you this back. I can't keep this.
I know.
Aesthetic earlier.
I would have been really sad if it hadn't worked today. Alright, last problem.
But the aesthetic is so nice.
So on
Alright, so thoughts.
It's kind of one of those no clue kind of things. Okay.
Oh, Jack, you want to
Do you know what sine of n does?
It goes to oscillator. It goes to oscillator.
How is that?
Oh, my paper's still in there.
Okay. Basically, when you don't have any idea what to compare to,
You're going to compare to 1 over n like I did on that other one. This is just one of the classic ones. I don't know what to tell you. But
I definitely don't know which one's bigger or whatever. I guess I could graph it and look at it, see if it was something from some point onward. But I don't just off the top of my head know. What does this guy do? Diverges. And I'm just going to say harmonic series. Okay? You can't. It's just something that I know how it behaves, and I'm going to compare it to it and see if I can get a limit. Because if I can, I can find the answer. So I'm going to do my sequence divided by the sequence I'm comparing to. And so as n goes to infinity, what does 1 over n go to? 0. And the sign of 0 is 0. Sign of 0 is 0, people. Go home and study it, please. All right. As n goes to infinity, this guy goes to. What's L'Hopital? The derivative of sine 1 over n is what? I know that you do, but it's not correct. Okay, times the derivative of the inside, so that's n to the negative 1. So what's the derivative of the inside?
Negative
1 to
negative 2. Jack was just saying, like, making noises.
I was going to wonder what that is, too. Okay. At least we'll have. Oh, that's true. That is helpful. Sometimes you don't get that for people. All right. So this guy is also n to the negative 1. So if I take the derivative. So now, as n goes to infinity, what does 1 over n go to? And so the cosine of 0. Finite and positive. So both behave the same. Therefore, our series diverges. And this is your homework, which is in the blue calculus book.
I will.